Good morning, and welcome to my Keystone presentation on planet formation across the galaxy. My name is Arnaud Michel, and today I'll be presenting to you preliminary results on how we'd expect planet sizes to vary across the galaxy. But before delving into that specific research, I'd like to give you a brief overview on star formation and planet formation to thus demonstrate how both of those are very much interlinked. It all starts out with a giant molecular cloud. This is a cloud of dust and molecular hydrogen, which is gravitationally bound. And then within this cloud, we have denser regions which will accumulate dust and molecular hydrogen under the effects of gravity to form clumps. These clumps eventually reach densities that are large enough such that gravity overcomes counteracting pressures such as thermal pressure and collapses to form a prestellar core. The prestellar core is huge. It's on the scale of 50,000 AU. In context, the distance between the Sun and the Earth is 1 AU. This is 50,000 times that. And so this prestellar core continues to collapse into a young small protostar, a class 0 object. The small protostar will continue growing in size by accreting infalling matter from the leftover molecular cloud around it. Eventually, it forms a fully fledged rotating star, class 1 object. This rotating star will then take the leftover material from the molecular cloud and flatten it out and make a circular protoplanetary disk around it. And so now we can see we're on a much smaller scale as it's on a 300 AU-like scale. And this protoplanetary disk, here imaged in orange, will evolve. It starts off as a slightly dusty and very gaseous disk, and over time, the gas will accumulate around the dust, and the dust will grow into millimeter-sized dust, centimeter-sized dust. We're now in a class 2 system. And this dust, as it continues to grow and form larger and larger size objects, we have meter-sized objects, kilometer-sized objects. We now enter a class 3 system. These objects will accrete and form planets and clear the dust and the gas into the composition of these planets. Thus, we have a planetary system. And this one is on the order of 50 AU. So we can see that this huge one giant molecular cloud has been essentially shrunk from all its dusty and gaseous components into the solid planets and the star. And so what is interesting for us is highlighting the relationship between the host star and the orbiting planets. What we're interested in is composition and how these two relate. So this leads me to the research I conducted at the University of Bern in the summer of 2019. In collaboration with PhD student Jonas Haldeman and professors Dr. Christophe Mortesini and Dr. Jan Alibert, we set off to investigate how different stellar populations within the galaxy could be expected to host, for the same planet type, different planet sizes. And it turns out it is the case. The planet sizes should vary by a couple percent between the different stellar populations. This led to us writing a research paper entitled Planetary Mass-Radius Relations Across the Galaxy, which has since been submitted for publication to the Astronomy and Astrophysics Journal. So what do I mean by these different stellar populations within the galaxy? We're looking specifically at what we call a thin disk, here in red, in which we are situated. Then we have the thick disk stellar population sandwiching the thin disk in blue all around. And then surrounding this, we have the halo. And so what we do is we sample thousands of stars in the thin disk, hundreds of stars in the thick disk and the halo, to look at what would be the expected planet sizes around these different stars in these different stellar populations. And why is it that these different stellar populations vary? It is not only in terms of their geographic location, but also in terms of their age, which in turn will lead to compositional differences, which we'll see lead to planet size differences. But what is it about these ages? So in context, the Earth is around 4.5 billion years old. And then we have the thin disk, which is 6.9 billion years old, the thick disk 8.7, the halo 12.5, the Milky Way 13.5, and the universe 13.8 billion years old. So we can see these are huge timescales. And for the thin disk, thick disk, and halo, these different stellar populations are of different ages, which means that they're expected to be of different compositions, because as the younger stars that are formed in the thin disk, they're formed from material that has gone several cycles of star formation and death. this leads to the enrichment of certain elements such as iron. And so how this translates to planets is the fact that the solar photosphere's composition is a good approximation for the expected solid planet bulk composition. What this means is that the solar photosphere, the outermost visible layer of a star, so when we look at the sun, we see a solar photosphere, its composition, specifically looking at iron, silicon, magnesium, calcium, oxygen, these are well reproduced in the composition of solid planets. For example, the Earth or Mars, or the meteorites in our solar system, which is how Lourdes 2003 got to this assumption. This assumption is the underlying component of this research paper because we're looking at how stellar compositions should be affecting planet compositions and in turn their sizes. So what are these planet compositions? We look specifically at iron mass fraction and water mass fraction within the different stellar populations. So we use stoichiometric relations to calculate these. And so we can see that in this table, the iron mass fraction for planets around thin disk stars is expected to be of 30.7%, whereas it drops down to 21% around halo stars. In contrast, the water mass fractions for planets around thin disk stars would be 59.7%, but then increasing down to 75.58% around halo stars. And so we're looking at how these different compositional variations would impact the planet sizes. So what do? We use two models and two planet scenarios. We use two models to confirm the results and validate these and check that this is not an artifact of a particular model. And then we use two planet scenarios to study one scenario at 0.1 AU iron silicate planet. So remember, 1 AU is the distance between the sun and the Earth. So this is a tenth of that distance. And so the planet is really close in, and it's got an iron core and a rocky silicate mantle. And then we have a planet at 4 AU. This is much further out. And so it's got an iron core, a rocky silicate mantle, and an icy envelope. And so how is it that these compositional differences come about? This is due to the bulk composition at the point in which these planets are assembled. Within the protoplanetary disk, the material very close into the star, for example, that will form the 0.1 AU planet, is essentially heated up and it sublimates out the ices, so we're left with the iron and rocky components. Whereas as we move outwards and past what we call the ice line or the frost line here, we have the ices that are conserved in the solid planet bulk composition and result in the second scenario, where we have an icy envelope. And so this leads me to looking at what these results look like. So here we present results for the 4 AU scenario, where we have the mass radius relations on the left-hand side, and on the right-hand side, radii distribution plots. So on the top we have for a particular model, and the second set of plots is a second model. So let's first look at the mass radius relations. Along the x-axis, we have masses, so from 1 to 10 Earth masses. And then on the y-axis, we have the radius in terms of Earth radii. And we can see that between the different stellar populations, the median expected radius is different between the thin disk, the dashed red, the thick disk, the solid blue line, and then the dotted orange line is the halo. And so we can see there's a difference. And so this difference is reproduced across both models, which gives us good confirmation of the results. But what does it mean that I say this median difference? When we look at the second set of plots, these radii distribution plots, we can see that for a particular mass, here 10 Earth masses, we're looking at how there's a distribution of expected planetary radii within the thin disk stellar population and within the thick disk stellar population. And this is because within the thin disk, the stars vary in terms of their composition. And thus, this results in a variation in terms of the planet radii that are expected around these stars. But between the thin disk stellar population and the thick disk stellar population, we can see that the distributions of radii overlap, but their median, shown in the dashed line, are different. And so this brings to the key component of these results, is that we can see it in the exoplanet statistics rather than in a singular case-by-case basis. We need thousands of planets to see this median come out. And so we can see these trends between the thin disk, the thick disk, and similarly between the thick disk and the halo stars and in turn their planets. And so this brings us to what it means. Between the different galactic stellar populations, there is an expected 0.5 to 3.3 mean difference in radius per mass across both models and both planet types. What this means is that between the scenario at 0.1 AU or at 4 AU, between the two different planet types, there is a minimum of 0.5% radius difference all the way to 3.3%. And these are the constraints. And so from these results, how do we go forwards in terms of our observations? So the Plato telescope, due to launch in 2026, should observe such mass-radius relations when it looks at thousands of exoplanets across the galaxy, namely not only observing stars and the exoplanets within the thin disk, but also within the thick disk and the halo. The latter two have had much less detections, although there are some, and thus Plato would fill in this gap and look for these thousands of planets, thus enabling to confirm these mass radius relations we see in the expected statistics. And so this leads me to the next point, is that when we look at these older exoplanets around old stars in the thick disk or the halo, which differ only by a couple percent in radius, this could open the possibility for the observation of an old Earth analog, which might differ in composition, but in terms of its size, for a similar one Earth mass, it would differ only by up to 3.3% in radius, which is very little. And so overall, this leads me to the fact that there's still so much more to observe and learn about planets and about our universe. And as such, I want to thank you, my viewers, as well as my Quest mentors, Dr. Ian Hoffman and Dr. Natalie Burston, as well as the co-authors and research supervisors of my research in Bern. And I would like to thank Quest University Canada and the University of Bern, and thank you again very much.